Welcome back to the Deep Dive. Today, we are taking a monumental stack of research and analyzing what happens when you combine black box optimization with hyperscale architecture design. We're talking about evolution strategies, or ES.
Mm-hmm.
It's always been this kind of dark horse, an incredibly robust alternative to gradient descent, especially when you're dealing with noisy environments or objectives that aren't differentiable.
It's incredibly powerful and it parallelizes beautifully, but let's face it, for years it's been strictly confined to smaller models.
Right.
The minute you try to scale ES to modern networks, I mean those massive structures with billions of parameters, you just hit a wall made of memory and compute costs that are frankly prohibitive.
And that wall isn't a subtle slowdown, it's a hard stop.
Hmm.
The reason is the sheer requirement of generating and evaluating those full-rank parameter perturbations.
Right.
You need a massive matrix, E, the size of the entire model, for every single member of your population. And you have to store and compute with thousands of them at once.
Exactly. You're just drowning in auxiliary storage and redundant computation, which severely limits your population size n. And if n is too small, your search just becomes inefficient and noisy.
So what's the mission today?
Our mission is a deep technical analysis of the project that solved this scaling crisis. EGGROLL, which stands for Evolution-Guided General Optimization via the Low-Rank Learning. This is how you take robust black box optimization and really make it competitive for an AI researcher working in that billion-parameter regime.
Okay, let's unpack the core fix. EGGROLL solution is it's deceptively simple in principle, but pretty revolutionary in application. It's about replacing that prohibitively expensive full-rank perturbation E.
With a low-rank approximation, that's the core mechanism. We move from E to E as approximately A-B transpose.
Right.
So instead of one gigantic matrix, we introduce two much smaller ones, A and B. And the key here is that the rank R is a hyperparameter you can tune, and it is orders of magnitude smaller than the model's dimensions.
So we're talking about an R of what, 10 or 20, even if your dimensions are in the thousands?
Exactly. It's sort of like the architectural wisdom you see in techniques like LoRa, but applied specifically to the noise vector in the evolutionary search, not the final weight update.
Okay, so what does that actually mean in terms of concrete, quantifiable savings for a researcher dealing with a massive model?
The savings shift the feasibility boundary entirely. Let's look at storage per layer. You drop from, say, times m parameters for the full rank matrix down to just times plus n for the low rank one. So if and n are both 10,000 and r is 10, you've just slashed your perturbation storage requirement by a factor of 500.
Wow. And I'm guessing since computations is so tied to memory access, the forward pass cost just follows that same dramatic reduction.
Precisely. The cost drops from big O of m to big O of r times m plus n. This efficiency, when you put it on a hyperscale GPU cluster, translates into a hundredfold increase in training throughput for billion-parameter models.
100-fold.
Yeah. To put that in perspective, that means you can iterate your complex hyperparameter searches weekly instead of, monthly or even quarterly.
That's massive leverage. The source material even notes that the speed approaches pure batch inference, which is a testament to the hardware-aware design. But hang on, here's the trade-off that a researcher would immediately flag.
I know where you're going with this.
If we only sample low-rank noise, aren't we severely restricting the search space? Aren't we compromising the quality of the final update?
That is the crucial technical nuance, and the answer is no because of aggregation. While the individual perturbation, EI, for worker I, is strictly low rank,
Right.
the overall EGGROLL update is an average over the entire population of N workers.
Right, because the full update is a sum of all those N low-rank matrices.
Correct. The final aggregated parameter update matrix has a rank of the minimum of N times R, M, or N. And since EGGROLL is designed for huge populations, we're talking N in the tens of thousands, the product NR becomes so large that the resulting update is almost surely full rank.
So you get the computational benefits of low-rank sampling without sacrificing the expressiveness of a full-rank update.
That's the clean engineering trade-off that makes this whole thing work.
That makes the engineering solid. Let's move to the math, because this isn't just a clever hack. There's a strong theoretical guarantee here. Let's start with the update formulation.
Right, the Gaussian EGGROLL update. It's MUT plus 1 equals MUT plus your learning rate times the average of all your perturbations, E weighted by the fitness function.
Okay, but that formulation relies on the perturbations having a controlled variance, right?
Yes, and because we're using this A-B transpose structure, if we didn't scale it, the variance would just grow unbounded as we increase the rank R.
So you have to apply that crucial scaling factor.
Precisely. The low-rank perturbation has to be scaled by 1 over the square root of R. So it's E equals 1 over root R times A-B transpose. This keeps the variance of E stable at big O of 1, which is essential for the whole search process to converge.
This leads us directly to Theorem 2, which is really the heart of the mathematical guarantee. It confirms that the low-rank update converges to the true full-rank update. But the convergence rate they cite is the surprising part.
It converges at a fast big O of 1 over R rate.
Right, using the Frobenius norm.
And that's mathematically significant because the typical convergence rate you'd expect from the central limit theorem is big O of 1 over the square root of R.
Okay, stop there. For researchers used to complexity bounds, 1 over R is dramatically better than 1 over root R. It means adding just a few ranks gives you huge returns immediately. Why the acceleration?
It all comes down to the symmetry of the chosen noise distribution. The researchers enforce this assumption that the perturbations are sampled from a zero-mean symmetric distribution.
Like a Gaussian.
Exactly. And when you have that symmetry, all the odd-order cumulants of the resulting distribution just vanish. They go to 0.
And what does that vanishing act do for the convergence rate?
Well, the approximation error in your gradient estimator is determined by the lowest non-zero higher-order cumulant. Because the third-order ones disappear due to symmetry, the error is controlled by the fourth-order term. This higher-order control gives you that accelerated 1 over decay rate.
That's a really elegant piece of theoretical justification.
It is, and the empirical evidence backs it up completely. The source shows convergence is near complete even for ranks as small as 10. So you get efficiency, stability, and this fast theoretical convergence.
Now, moving from the theory to the metal, the high throughput isn't just about the math. It's about exploiting the GPU architecture.
Specifically the tensor cores on systems like the NVIDIA H100.
So the forward pass, that evaluation of the perturbed model, has to be handled in a very specific hardware-aware way. And the key is an algebraic decomposition.
That identity is the engine of the speedup. It's x times mu plus sigma e equals x times mu plus this perturbation term. It lets you transform one large matrix multiplication into a sequence of smaller, batched operations.
Let's break that down. The first term, x times mu, is just standard batched matrix multiplication, which hardware is already great at.
Right. But the second part, that perturbation term, is where the real speed gains happen. Walk us through that sequence.
Okay, so the first operation is the matrix vector product, xi times bi. And since b is really narrow, only r columns wide.
This becomes a set of batched, low-dimension matrix multiplications. Critically, these are extremely efficient on modern tensor cores.
And the output of that is a small vector, which then gets multiplied by AI transpose.
Exactly. The second part is basically a batched scalar vector multiplication. These are sequential operations that avoid the huge overhead of calculating a full BAMS by a matrix E. By decomposing it this way, they achieve throughput equivalent to running maximum batch inference.
I see. That structure, breaking it down into two narrow matrices applied sequentially, that's the exact principle used by optimized inference engines like VLLM for batch Loira inference.
That's absolutely right. They've managed to turn ES training into an inference-optimized workload.
What about memory?
Another critical innovation. They avoid persisting any of those large perturbation matrices. Instead, they use a counter-based deterministic random number generator.
An RNG.
Yeah. This lets them reconstruct the noise on demand for the forward and backward passes without holding those massive E matrices in GPU memory. It's another huge auxiliary memory saving.
This engineering flexibility training fast without backpropagation, it just opens the door to domains conventional methods can't touch. Which brings us to this fascinating case study, the EGG model, the Evolved Generative GRU.
This is a perfect showcase of ES as a black box optimizer. Because EGGROLL is gradient-free, the researchers could design a model constrained purely for inference efficiency, completely disregarding the headaches of, say, backpropagation through time.
So the EGG model was built with three constraints that really pushed the limits of the hardware. Let's look at constraint 1, pure integer training. What does that mean specifically?
It means all weights are strictly innate, all activations are integers, and there is zero floating point casting during training. They use in-8 matrix multiplication with in-32 accumulation, which is the fastest path through the tensor cores on H100s.
So peak speed, but trying to train that with floating point gradients would be a nightmare.
Impossible, or close to it.
Constraint 2. A nonlinear RNN variant, the min-GRU, instead of a transformer. Why a recurrent network?
Well, transformers are great for parallel processing, but RNNs are essential for compact state tracking. But they usually suffer from gradient instability, especially BPTT. Since ES bypasses that problem entirely, they could pick an RNN purely for its architectural simplicity and memory efficiency.
And constraint 3 is maybe the most unconventional. The removal of all explicit activation functions. No ReLU, no TAN, nothing.
This is wild. They found that because they're using pure intake calculation, the saturated addition of those values provides enough nonlinearity through implicit clipping.
So when you overflow the 8-bit integer boundary, that clipping acts as your nonlinearity.
That's it. A standard gradient system would struggle desperately to use that for learning, but the blackbox ES method is flexible enough to exploit it.
So EGGROLL enables stable pre-training of this highly specialized non-differentiable model. And what was the impact of scaling?
It allowed them to scale the population size up to over 262,000 unique perturbations. That is 2 orders of magnitude larger than previous state-of-the-art ES works.
And the ablations confirm the core belief of ES, right? That scaling the population is directly tied to performance.
Absolutely. The ablations show that maximizing those unique perturbations is critical for pre-training performance. This confirms that to make gradient-free pre-training work on these kinds of constrained architectures, a highly scalable ES method like EGGROLL is non-negotiable.
Okay, beyond the EDG model, let's quickly touch on performance in more traditional domains. In reinforcement learning.
In RL, it maintains competitive performance against standard OpenES, but with substantial speedups. We're talking up to 40 times faster in environments like Jumanji Snake when comparing against a full rank update. You get the quality policy, but in a fraction of the wall clock time.
And for LLM fine-tuning on complex reasoning tasks.
There, EGGROLL was competitive with strong gradient-based baselines like GRPO using RWKV7 models.
But the scaling advantage must have been huge.
Stark. On the countdown task, for example, EGGROLL's facilitated over 1,000 parallel generations per GPU. Compare that to GRPO, which was limited to just 32. This ability to explore a search space that's over 30 times larger simultaneously is why ES, when scaled by EGGROLL, is a real competitor even in the LLM domain.
So to synthesize this deep dive, EGGROLL took evolution strategies, a powerful but scaling limited method, and made it hyperscale ready.
They did it by using that low-rank A-B transpose perturbation structure, which dramatically cuts memory and compute costs, often by more than 100x.
And this engineering breakthrough is mathematically justified, proven to have a stable, fast, big O of 1/Er's convergence rate because of the noise symmetry.
And this combination of theoretical rigor and hardware efficiency is what allows EGGROLL to unlock completely new architectural territory. It enables stable pre-training of things like that purely integer EGG model that backprop systems just couldn't handle.
The source material suggests EGGROLL can be applied to large-scale neurosymbolic systems, or complex control systems that are often riddled with non-differentiable components. So for you, the AI researcher deep in this space, here's the big question to consider. If gradient-free optimization becomes this scalable and efficient, how might this fundamentally change the way you design neural architectures? If you no longer need end-to-end differentiability, what complex constraints, bespoke operations, or nonlinearities previously thought too messy for floating point math now become fair game? That shift in design freedom could be the next massive frontier.